All right. Hey, everyone. Thanks for coming. Today we're going to talk a little bit about accelerating ZK and FHE on our custom silicon processors. So basically, for those of you who are new to fabric cryptography, we're a company building custom silicon for programmable cryptography. So, we think that the next generation of general purpose microprocessors is going to be focused on programmable cryptography, like ZK and FHE. So just like the CPU revolutionized personal computing and the GPU revolutionized 3D graphics, we think that the VPU is basically the next era of microprocessors. And thus far, we've focused a lot on ZK, so we've done a lot with our partners, our protocol partners in the ZK ecosystem. So we've worked with Polygon, we've worked with Reciro, working with a few others. And basically, this is our Plunky 2 performance. So you can see there's a very, very big performance boost, orders of magnitude, that you can get with custom silicon. And we are thinking of bringing the same thing to FHE. From the beginning, the thesis with the verifiable processing unit was that basically you could create a general purpose processor that could accelerate all of the above, right? So it was never meant to just be a ZK processor, it was also meant to target FHE. And because FHE actually uses a lot of the same operations, basically you can reprogram the VPU to do a lot of the same things. So in particular, if you look at FHE, you have a lot of shuffling of things, you have NTT, some amount of linear algebra, these are all things that the VPU is good at. And, neither kind of GPUs, CPUs, or systems with both are really built for cryptography, right? In FHE, we also have FPGAs. But all of these things essentially operate on very small amounts of data, right? So they operate on amounts of data that are, int32 or below, right? And the thing about that is 90% of your die area is dedicated to things like floating point arithmetic or things like that. And so, all of the existing processors really aren't dedicating most of their transistors to things that are relevant to programmable cryptography. That is the problem that we're fixing. So this is a little photo of our architecture, right? So on the right, you see a RISC-V CPU. That's an 8-core RISC-V complex capable of booting Linux. And then on the left, you have a big array of tiles. And every tile has a massive vector processor that can do a lot of modular arithmetic. And so basically, you have lots of GDDR, high bandwidth memory, essentially, around the chip. We have an aggregate of 1 terabyte per second of memory bandwidth per card. And so this is pretty much built for exactly the kinds of arithmetic intensity found in programmable cryptography workloads. And these tiles that are designed for prime field arithmetic are pretty much arranged in the die and stamped out 40 times per die, 120 times per card. So you just have thousands of modular arithmetic units per card. And so another thing that's kind of more relevant for ZK, but also relevant for the ease of programming on this thing, is that the interconnect between the CPU and GPU is ultra high bandwidth. It's 7 terabytes per second. So you can move data in the chip in an ultra fast way. In particular for FHE, if you have operations that operate on a bigger amount of data than you can hold in each tile scratchpad, then what you can do is you can shard them across multiple tiles and communicate between them in a software-defined kind of data flow way. So how does this actually get programmed, right? You might ask. Well, on the left, you see kind of modular arithmetic instructions on the GPU, right? So the VPU is essentially like a GPU, right? You'll decompose your workload into a bunch of parallel instructions, and then you're going to run those instructions through an instruction set processor, right? So it works almost exactly like a GPU, and essentially it just takes fewer operations on the VPU. So you're taking the equivalent of a lot of those operations and shrinking them to maybe like one, 32 or 64-bit modular or arithmetic kind of instruction. And so, as a sample of the kinds of speed that you can see on the VPU, we did this benchmark actually for a ZK workload. There's a 2 to the 16 NTT that we profiled on 64-bit numbers. A V100 GPU can do about 300K NTTs per second. On a VPU server, you can do 21 million NTTs per second. So this is the kind of NTT performance that we're bringing to the ZK space, but we're also going to be bringing to the FHE space. And so as kind of comparison in the specific context of FHE, we actually did a study for Zama. And basically for a uint64 mult in FHE, the VPU is able to hit a tiny fraction of the execution time per mult at way lower costs per hour for an overall cost advantage that, compared to the H100 is over 100 times better, and compared to a CPU is over 20 times better. So, you're getting orders of magnitude performance advantages or cost performance advantages beyond CPUs and GPUs. And the great thing about the VPU is it's not just tied to one specific FHE scheme. Just like we support all sorts of different ZK-proof systems, we support things that use, Poseidon, we use different hash functions, it doesn't matter what you choose. You can change the blow-up factor of your ZK algorithm. Well, just like that in FHE, no matter how the field evolves, no matter, what different kind of FHE schemes come out, you'll be able to switch to those and basically software reprogram the VPU. So the great thing about the VPU is it's not an ASIC, it's not kind of a hard-coded, hardwired thing. You basically have this fully programmable general purpose processor. And, there are some really fun plans we have for Gen 2, which is actually going to have even greater capabilities that are more relevant for FHE. There will be architectural improvements. We plan to do a great amount of software hardware co-design with the programmable cryptography community. The work that we did on Gen 1 really focused on ZK, but we plan to look a lot more at FHE. As a little teaser, we project that if we were on 7 nanometer, which we haven't decided yet, that we could potentially have 1 billion NTTs per second on a server. So that is the kind of performance advantage that you'll get even from VPU Gen 1. Given our updated designs. And so since we're taping out soon, we're basically starting that Gen 2 design process right now with a select set of partners. And this is the kind of performance boost. So if you look at FHE, right, like it has this kind of 100K or million times overhead versus plain text compute. Gen 1 is able to bring that down a few orders of magnitude. Gen 2 is probably able to bring that a few more orders of magnitude. We're getting into the range where ZK is right now, So basically our goal is with every successive generation to move the field forward the equivalent of, 5 to 10 years of evolution in the software or algorithm space. And yeah, that's it. Any questions from anyone?
So curious about the timeline for FHE support here. What are we looking?
Yeah, that's a great question. So we have NTT kernels that are super optimized already that we built for ZK. So hypothetically, if we were to focus our software team on FHE support, it could get done in a fairly good amount of time. It just depends on market demand. So actually, my question to you would be, what are you seeing out there? And I'm curious,
Yeah, so I guess on our end, we are planning to go live Q2 next year. Today, we're considering using GPUs. So the cost has gotten down quite significantly as well. They're about like $1.50 per hour, which is, it's a fairly good price, I would say. but yeah, if there are better alternatives, then yeah, of course, we'll be interested in learning more. And yeah, and I think the multiplication actually looks very promising, a lot more promising than I originally thought. So yeah.
Yeah, I mean, I'm looking forward to seeing it all happen, and I think it'll be really exciting to consider this. Past the first wave of ZK applications, we're going to be looking at it very seriously, and so super curious to see next year how it evolves.
Is this going to be available as a, like, can people buy the hardware directly, or would it be more like a hosted cloud service, or how are you guys thinking about this?
So we actually offer both. So there's a hosted model where you can kind of rent it from us, right? And then there's you can buy it directly, in certain quantities and then host it yourself.
Cool, another question.
Thank you. My question is related to, because you're building like a generalized chip like that can do ZK and FHE. Is there no performance loss by not building something that's hyper specialized for FHE?
Yeah, there's actually not. And that is part of the kind of secret sauce of Fabric. So if you look at the tile that we showed, right? Basically, this tile has a bunch of multipliers and adders and things like that. And the really cool thing about doing it this way and having an instruction set is that it turns out that when you have such big multipliers, like when you have only int32 or higher, right? You just have so much circuitry that the control overhead and the overhead of having a general purpose processor starts to go lower in percentage versus just the area that it takes to do the things that you would have to do in anything, right? Like no matter if you're supporting ZK or FHE, no matter like what kind of thing you're optimizing for, you're gonna have to have, some registers, you're gonna have to store data, right? You're going to have to multiply numbers, right? Like, so kind of the things that you inevitably have to do take up most of the resources of the chip, and then the things that kind of select between them are very, very minimal in comparison.
Got it. And my second question is more on the demand side for these chips. Like, I get it, like in the academic sense, like I'm pretty sure there's quite a bit of demand, but like from like actual people wanting to buy this for use cases, like where is that demand coming from at the moment?
So the demand is really coming from two sets of folks. A lot of ZK is happening right now. People are, for example, Polygon is prepping for the AG layer to go live very soon, and there are going to be pessimistic proofs. There are going to be a lot of proofs associated with transitioning the proof of stake, into ZK, and like there's a lot of things like that. RISC-0 has a few major partnerships also coming out. They're going to have a lot of cycles of demand for their ZK VM. So that's kind of one area that we're seeing demand. And then we also see demand from people who want to participate in these permissionless kind of proving networks. So far, we haven't looked at kind of FHE demand, but it sounds like maybe that'll also be a thing next year. But the demand up to now has been kind of from the ZK space.
And not from the like Web 2 TradFi sort of world?
Web 2 moves at a different pace, let's put it that way. So, there is demand that we're seeing actually. Someone came to us from JP Morgan Chase a few weeks ago, and they were saying actually that they had 7 use cases ready to go, and they just wanted the hardware to be ready. But, those folks typically will do a small, commitment and do a pilot run and stuff like that. We're seeing much more like immediate demand in crypto. But I think as institutional adoption continues over the next 2 to 3 years, you'll see that picture change drastically. And ultimately, I think it's going to be a really, really big, fraction of the market.
Got it. Thank you.
Awesome. Okay, another question.
Hi. So a couple of questions. One is that are these available today? And like if we were to build our own deployment for it, what would be the cost of the card, and what is the hardware stack that you need to run alongside with it? Is like what kind of CPUs and what kind of memory do you use in the entire system?
Yeah, that's a really good question. You don't have to take care of those things. Actually, we sell the whole box. We have a whole box design, and we basically plug these as PCIe cards into the box. Eventually, hopefully people have this maybe at home and stuff like that, but right now, this is sold in kind of a server format. So each server is about, 3 kilowatts or so, and you're plugging these in standardized kind of 19-inch racks, in rack-mounted data center format. So that's kind of the current format of it. Does that answer your question?
Sure. And like if someone were to experiment with it today, they want to develop and test out these, is there some kind of development kit that you offer or access to your servers?
Yeah, the dev kit will come out when the servers come out. And right now we're still in the middle of developing that. So, for new hardware, it is a journey to kind of create a new SDK and like have the NVIDIA spent, 15 years developing CUDA, 20 years developing CUDA to where it is today. So, it takes a while for that to mature. So I wouldn't anticipate that the developer experience is super awesome from day one. If you want to develop your own kernels. On the other hand, if you want Fabric to develop kernels, that's a fairly straightforward process. All we need to, kind of see is like, hey, there are users, they're going to benefit from it. Then, we would be able to actually do that and release, basically these kernels on top of our hardware.
Okay. And the last question is that you mentioned that it has very high performance for high precision computation. What about traditional like simple floating uint8 and 16-bit operations? Did you benchmark that? Is it comparable to industry?
We have 0 performance on those things.
Okay.
That is intentional because it allows us to dedicate all of our die area to the things that matter for cryptography. So.
Okay. Yeah. Thank you.